complex build is distributed with a predefined ligand database. But what if you cannot find your ligand of interest in the database? Well, there are two ways of addressing this situation. If your lanthanide complex ligand has already been described in an article, the easiest way is to go to the complex build suggest a new ligand webpage and fill out the form. We will provide an update to our database with your ligand in it as soon as possible. But if you cannot wait, or if you are interested in a novel ligand never before published in a lanthanide complex, you can easily add this ligand yourself to the complex build database. Let us now see how to do that. Complex build has a button called Add a new ligand to the database that opens a widget in which the user can add a .mol2 file of the new ligand to the ligands database. Besides the .mol2 computational chemistry file, complex build further expects to receive additional information about the new ligand. Which atoms correspond to its teeth? What is its charge, symmetry, IUPAC name, and short identifier? But, actually, the only demanding part in adding a new ligand is the creation of its complex build compatible .mol2 file. So, let us now explain how to do that. A .mol2 file of a ligand can be created using any molecular modeling software that has this capability. So, you can do that by using any proprietary softwares such as Gaussian or HyperChem, or any free molecular modeling softwares such as Avogadro. In this tutorial video, we will use 5 different softwares, all 5 are free for academics, to create our .mol2 computational chemistry file of a ligand: Avogadro, MOPAC, TextPad, OpenBabel, and ACDChem Sketch. Please make sure that you have all of them installed and running in your computer before attempting to reproduce the steps described in this video. Let us start with Avogadro. There are many YouTube tutorials on how to use Avogadro to create new molecules. In the description of this video, we provide links to some of these tutorials. Okay, so let us assume that you need to add the following new ligand to the database: a substituted beta-decatenate. In Avogadro, with the Draw tool, first place the carbon atoms of the ligands, then the oxygen atoms. After that, replace the hydrogen atoms of the methyl groups by the fluorine and chlorine atoms. Now, very important. Please note that the ligand must be in a conformation that can be coordinated to the metal ion. For example, our substituted beta-decatenate must be in a cis conformation to be coordinated and not in a trans. Therefore, we must adjust the conformation accordingly. To change the conformation of the molecule from trans to cis, first click on the selection tool and select the group of atoms to be rotated. After that, click on the manipulation tool and grab the atom around the other atoms that will be rotated. Now, rotate the atoms, holding the right side of your mouse. Please, do not forget to add the alternate double bonds of the beta-decatenate. Finally, coordinate the ligand to the proper lanthanide metal. In this case, we will coordinate this ligand to europium. In the view label, go to the Properties drop-down list and then click on Atom Properties to set the formal charges of the atoms to the correct ones. Now, we must pre-optimize the geometry of the system with the Universal Force Field, UFF. Click on the Auto Optimization tool button, set the force field to UFF, and then click on Start, and wait until the optimization terminates, that is, when DE is equal to 0. To conclude this initial part with Avogadro, click on Extensions and then on MOPAC to generate a .mop input file. Set the method to RM1, set the format to Cartesian, and please do not forget to set the correct charge of the molecule, in this case +2, because our ligand has a charge of -1 and europium a charge of +3. Now that we have a .mop file of our ligand, coordinated to a lanthanide ion, it is time to optimize its structure in the MOPAC software. Before doing that, open the .mop file and add the keyword XYZ at the end of the first line of the file to guarantee that the .arc file will show the final geometry, also in Cartesian coordinates. Now, submit the file to MOPAC. After running the file with MOPAC, please open the .arc file and go to the bottom lines to copy the Cartesian coordinates. Put them in a text pad file. Replace the first 3 lines with 2 blank lines, and in the first of these 2 blank lines, specify the number of atoms of the molecule. In this case, our complex has 15 atoms. Now, remove the +1 or -1 symbols between the coordinates of each atom. That is easily done with TextPad software by selecting the column. To enable this feature in TextPad, click on the Configure label and then turn on the Block Select mode. Then, save the file with the .xyz extension. Now, go to the Open Babel software and submit the .xyz file as an input file and convert it to a .mol2 file. Save the .mol2 output file with a name of your choice. Now, let us return to Avogadro. Yes, that is a long journey, but we are almost there. Please, be a little more patient. In Avogadro, open the .mol2 file, remove the lanthanide ion, and then save it again as a .mol2 file. Please, notice that .mop and .xyz files do not contain information about the topology of the molecule. When the Babel software converts each of these files to a .mol2, the connectivity of the atoms is simply inferred. But that topology might be incorrect and thus in need of correction. If that is the case, you must modify the connectivities manually. They are in the final part of the .mol2 file preparation. In the case of our substituted beta-dicatin, we must set the beta-dicatinate bonds as being delocalized bonds by indicating them to be of the AR type. To do that, let us return now to complex build. We will use its ligand visualizer to determine the numbers of the atoms with delocalized bonds. Click on Add a new ligand to the database and click on Choose File. Now, go and open the .mol2 file. The ligand structure is shown on its viewer window. Please examine the structure carefully to see if the connectivities are correct and if the delocalized bonds are being recognized as such. In the case of our ligand, we can see that the beta-dicatinate bonds are not set as delocalized. Let us fix that. Notice that the number index of the atom is shown when the mouse is passed over it. Further, your cursor will also change to a small hand. Please annotate the numbers of the atoms whose types of bonds will have to be modified. For example, in our present ligand, we must set bonds between atoms 14 and 7, 7 and 6, 6 and 2, and also between 2 and 13 to the R type. Now open the .mol2 file on TextPad and change the types of bond accordingly. Save the file and open it again on Complex Build by clicking on Add New Ligand to Database and then on Choose File. Confirm that all bonds are now correct. OK. We can now proceed. Now, select the teeth of the ligand, that is, the atoms that are to be coordinated to the metal ion of the complex. That is made by clicking on these atoms on the ligand visualizer window that is being shown. When clicking on a specific atom, a highlighted green circle will appear around it, indicating that it has been selected as a coordinating atom. The user can select as many atoms as necessary. Of course, the number of atoms that have been selected defines the denticity of the ligand. To deselect an atom, the user simply needs to click on it again, and the green highlight circle will disappear. With the correct atoms selected, the teeth entry is automatically filled with their indexes. Please take note that, at present, Complex Build only supports ligands that are coordinated directly by atoms. Next, the user has to pass to the software the charge of the ligand. This is made by clicking on the drop-down menu, Charge, and by selecting one of the integer values available. In our case, the charge is -1. Now, the user must inform the ligand symmetry to the software. If your ligand is monodentate, just click on the letter A, and you are done. However, if your ligand is bidentate, its symmetry can be either AA or AB. If there is no chemical difference, if you flip over the ligand by switching the coordinating atoms, then your ligand is of AA symmetry. Otherwise, if the chemical arrangement is modified, if the coordinating atoms are flipped over, it is of the AB symmetry. The ligand in our example is of the AA symmetry. Now, the user must type an extensive name for the ligand in the field name, preferably IUPAC. That is an important descriptor, since each ligand must have a unique name. To generate the IUPAC name, we can use the ACD-Chem Sketch software. We simply draw the ligand on it and then click on Tools. Then, on Generate. And finally, on Name for Structure. We can then copy that name and paste it on the name, preferably IUPAC, on Complex Build. Finally, the user may pass a short identifier abbreviation of that ligand to easily identify it on the ligand database. Ideally, that should be an acronym that is widely recognized by the lanthanide scientific community, such as DBM or DMSO. If that entry is left blank, complex build will fill it with the IUPAC name passed before. So, that is it. The ligand can now be added to the database just by clicking on the Add New Ligand button. You are done. Yeah. The ligand is now available to be used to generate starting structures of lanthanide complexes with full stereochemical control. Thanks for watching this video. Have a nice day.